So I'm going to talk about our effort in building digital twins in two different paradigms. And I thought there's a moment I thought we switched completely to a different paradigm, but then later I realized that's not the case. So I'll just explain both of them. Okay, the problem is very well defined, right? So when you, at least the theme of the workshop is, you have images or you have some visual observations or you have even multimodal observations, but then you want to get digital twins out of it. And you see the pixels, we understand, to make it digital twin, there's an underlying causal process, right? So objects have geometries and materials and motions, and physics engines, they take these states and they simulate it and produce the pixels. So in the sense of digital twin or computer vision in general, is, okay, I want to invert the process. I want to reconstruct and build the distribution ideally of the geometries and materials and motions. These are things that we call like physical object intrinsics. You can de-render, revert the process, and then just like as people say many years ago, like vision as inverse graphics, you invert the process, you get objects attributes you care about, and then you can use it for a lot of different things. But how can we get that? So unlike cases like images and language, you have so many annotations. I think a big challenge is it is actually very hard to get annotations for all the things you care about, right? So maybe you still have some annotations for object geometry, but there's almost nothing about materials and motions and stuff like that. So how can we do that? So we explore two paradigms. The first paradigm, I call it in some senses like a physics simulator in a loop, or which is more like self-supervised learning, in the sense that, okay, think about it as an autoencoder, right? I want to encode the scene representations or visual interpretations. I got the things I care about, like geometry and textures, and then I decode it. But because I don't have supervisions, right? I don't have annotations on object materials and geometry. So what I can do is, okay, I can do self-supervised learning because I know these things are not, I have some prior knowledge of them, right? They're not like coming from nowhere. I understand by studies in computer graphics and physics simulation, how objects, materials, and geometry are supposed to interact with each other when there's lighting conditions and camera conditions. So I should be able to approximate the simulation process nowadays, especially in a differentiable way, so that I can have an end-to-end learning system that is fully differentiable. And then I can just use my reconstruction laws as a self-supervision to help me to discover the objects or attributes I care about, so that I can build digital twins with object geometries and materials without even having annotations. And during training, I can train on unannotated images and videos. And during testing, I can even just take the first half and take an image and convert it into 3D. Right, so this approach has a lot of limitations, but it also has some benefits. So just very quickly, I can highlight some examples of our effort here. In this case, we only have a single image. It's a single image of a bouquet with 50 different roses, roughly 50. And so we asked the question that is, okay, what really makes a rose, right? Why does it look like a rose, and why this is rose, but this is a cup and this is a microphone? So what's the difference between a rose and a microphone, for example? And we realize, we're seeing all these different instances. So they're like different instances, but they share the same object category. And what they're really sharing by sharing the same name is the fact that they share this underlying distribution of object intrinsics, right? So you can think about it as what is a rose is there's an underlying distribution of object geometries and textures, which I want to learn and model. But once I can discover from that, and in every instance here, I can imagine I'm just getting a sample out of it. And I can put that together with extrinsics like lightings and camera parameters, and I get to render them so I can see the roses in different forms. So we actually did that, right? So we just use this very simple observation in the device. We try to learn this distribution, and then we can sample from it. And then we put that into a differential rendering framework. You get a shape of beetle, you put it into certain lighting conditions and camera poses, which itself, can be a distribution to learn to be sampled. But in this case, you can probably approximate it pretty well using some heuristics. And then you get a shading, so you get appearance, and you get a fake image. And our goal is, of course, to make the fake image, because it's generated pictures, to be as close as the real images. And back then, because this is 3 years ago, we just use the discriminator laws, but nowadays you can use diffusion powers and stuff like that. So just to make sure that, okay, you're using this very weak guidance, but with knowledge about how physics are supposed to interact with each other to discover and build these digital twins with objects, material properties you care about without annotations on them. And after you have discovered this distribution, what you can do is you can see objects from different viewpoints. Now using this, you can see them under different lighting conditions, as seen in the second to bottom row as you're learning the material, the reflectance. And because you're learning a distribution of these objects, you can sample different instances of it. You can see the different sizes in the middle. Right? So you may feel like the results here are like not the best, but two clarifications. One is this is done 3 years ago, right? So there's no like diffusion priors and stuff like that. And second, which is more important, is we learn everything from this one single image, right? So there's one image as the input, and there's no pre-training or anything at all. Can you see my mouse? Well, you can't really see my mouse, so I'll move here. Okay, there's no pre-training at all, right? You're just learning from a single image without using any pre-trained models. There's no dino features and anything, right? So you just learn just from a single image. You can see that with proper inductive biases, you can actually get a lot just from a single image. You can learn so much out of it. Okay, so this is my PhD student Ranger. Okay, so after that, we thought about, is it possible for us to move beyond from a single object categories to multiple object categories? Because object categories are also not independent, and they share something. So in this work, which is led by my PhD student Jiajun, but also my then postdoc, Elliot Wu, so what we wanted to do is to discover knowledge of the geometries and textures, but also their articulation. They share the articulation behind these 100 different categories of animals, but they're all quadrupeds. So there's no snake, there's no fish. There are 100 types of quadrupeds, but can we actually learn the underlying distribution of their geometries and textures so that I can reconstruct them from a single image? I can generate and sample these different objects as well as their shared skeletal structures. Right, so in this work, we call learning 3D fauna from web. We just take internet images and videos of animals of different object categories and try to learn distribution out of it. Okay, so we also applied some, now after that, we explore some extension to the rigging representations because in digital twins, you want to make it work not only on rigid bodies. Now you have the shared skeletal structures, but how can you animate them, right? Especially if you think about, if you focus on these articulated objects. So, the rigging representation at a high level is you want to have an object, you have a statical structures, you have a skinny weight, which is also to be discovered, and then you can edit them so that you can get things like that. So in a follow-up work to the animal thing, which is in 2025, this year's CVPR. So we did this work called Category-Agnostic neural object rigging. It is also having this kind of I would say, self-supervision-like flavor in the sense that you want to encode the scenes into latent representations. It's a neural thing, but in some I wouldn't use that word. It's a compositional implicit representations in the sense that you encode it into a number of these. You can see the blobs. And then you can do some editing and you can decode it, right? So similar to the rows case, but now you have some rigging structure in the middle. You have the edited results. And you want these encoders of different object categories. Now it's even beyond quadrupeds. You have quadrupeds, you have fish, you have grasses, you even share the same architecture. But then you want to do unsupervised or self-supervised training with the blobs. But now, in addition to just like rendering objects, roses in the particular lighting conditions and make it look as similar to rows, you can separate what is the intrinsic properties of objects, including their scaling or opacity and stuff like that, from their extrinsics, which is the positions and rotations, which means you can then change the rotation or position of specific blobs, but keeping the intrinsics, right? So then this allows you then this indicates that after editing, the objects should have the same identity. It should be the same object, same appearance, but maybe with slightly different pose because one part of it has been moved. Right, so this allows you to go from this kind of original input shape and a slightly deformed shape to do self-supervised learning, right, which is very similar to the rows case, but now you have additional rigging structure in between. And the output is also the reconstruction not only geometries, but and the skeletal structures, but also these blocks that allows you to do object editing. So you can get an input image, you can get these compositional implicit representations, you can move them. Again, all these are learning without annotations. And you can scale a part of the objects. You can remove part of our objects so that you can edit, let's say, the length of the leg of the bear. You can even do some auto distribution generalization. You can synthesize objects that you've never seen before. So this is done by, again, Elliot, who's then my postdoc, and now he started as assistant professor at Cambridge. And Chen, who is my PhD student, and Guangzhao, who is back then a visiting student, and now is a PhD student at Cornell. So as a related effort, we also, this is a Microsoft bug with Windows then, because on Mac, I didn't have this problem. Okay, I wish they can fix that. But anyway, this is we built a data set of rigged object state. So by filtering Omniverse. So you take Omniverse extra large and do some filtering, and then as a related effort, we collected this data set of objects of different types that can be rigged, which can be potentially useful for training, for example, before models nowadays that people care a lot about it. Okay, so this is paradigm one, right? So I have physical simulating loop, which I originally thought it was great in some ways, and it has some limitations. But to be honest, I think it delivered has a more potential than I have originally expected. But it still has a lot of problems, and I think the problem a lot is actually tied with the use of the simulator. Now, simulator is great because it allows you to end-to-end training, especially when it's differentiable, but also because of that, it comes with some constraints. Now, first, it has to be differentiable because you want to do self-supervised learning. And there are a lot of things that can not be really made differentiable or can be made differentiable, but you have to make a lot of sacrifice in the type of approximations needed. And the second, you want it to be pretty accurate, and which is fine, if you look at specific object domains like single object. But when there are multiple objects of different matters, like soft bodies interacting with rigid bodies, with fluid, that's very hard to make it accurate. And third, because you have it in the loop, it has to be really fast, right? So in computer graphics, there's like all these differential ray tracing methods, which are surprisingly accurate, but they're just so slow. And here, if you want to do end-to-end training, you have to keep doing feed-forward and backward passes, right? The gradient has to pass. So you want every simulation step to be maybe no more than 100 milliseconds. And sometimes there's a just trade-off between how accurate you are and how fast you are. You just cannot have both. So it has a lot of these constraints, so it leads to some issue that is, for a lot of work I've shown, they work with certain assumptions. When the assumption is satisfied, that's great, but they are assumptions. For example, there's often a single object, there's a clean background. Sometimes you make assumptions on lightings or on the rigidity of the objects and stuff like that. So can we do better? And at the same time, this is also the moment that we have seen all the advances in the foundation models, right? Vision language models or video diffusion models just keep getting better. And I think, of course, these models still have some problems in different ways, and they may keep having those problems. But it's clear that they're getting better and they're very powerful. And for example, a video diffusion model, if you can generate such beautiful videos, despite there are cases where you have physical inconsistency, you must have learned something about object geometry of physics. So the second paradigm we explored is it possible for us to do physical grounding of these visual simulators, right? So if I just take these end-to-end pre-trained vision foundation models or image diffusion models or vision language models and try to discover, how much I can do grounding, I can ground them so that I can have not just a visual simulator or video simulator, but a physical simulator. So getting a physical simulator out of a visual simulator. So I want to maybe highlight one work that we did this year's CVPR in this paper and called Births and Deaths of Roles. So what is going on is we extended the previous work on roses, but now we try to discover another level of intrinsics to make the digital twin more vivid in the sense that you want to also capture its lifespan, right? So roles, you can have objects, geometries, and textures, you can relight it, you can do novel synthesis, but now you can also render its growing and wilting process. The light is a bit too strong, but you can sort of see it. Okay. And you want to model the lifespan of not just roles, but also other types of objects, including a burning candle, and a melting ice cream, growing sprouts, and a baking bread. You can see the bread is being baked, and then you can do novel synthesis, you can do writing, you can see how the baking process. So what is behind these physical phenomena, and what are the problems we want to address here? Right, similar to the roles case, we want to discover object intrinsics, but there is environmental conditions, there are static assets, but the novel thing here is we want to also capture its dynamics, right? So we want to get dynamic 4D assets or dynamic 4D digital twins out of the visual input. And the dynamic objects include, so across all these different domains, but if we decompose them a bit further, then it includes evolving geometries, evolving albedo, evolving materials. So these are the intrinsics we've worked on before, but now you want to capture the dynamic process, so they are evolving. So we call this the temporal object intrinsics. And then similar to the static cases, you can put them together with environmental conditions and backgrounds and lightings, and you should be able to re-render and generate objects, but now you can generate in 4D. Okay. So the question is now, how can we automatically discover and create these temporal object intrinsics for different phenomena, maybe with the guidance from image or videos? And so the problem we want to solve is actually very similar. It's a simple extension of the problem we solved before, but the approach we take turned out to be now quite different. That's why I say there were two different paradigms. So unlike we're doing self-supervised learning, which in some sense is still self-supervised learning, but unless we have physical simulator in the loop, that we have a differential rendering, we still have some differential rendering, but now we rely a lot on distillation. But due to distillation, we realized, of course, just like there's no 3D data, there are even fewer 4D data, right? If you search for blooming rows on the sketch value, you just get nothing. But you do have a lot of 2D data informing object dynamics. For example, if you search a Google image of a rose blooming, you get a lot of the roses. You can even get some time-lapse videos and stuff like that. Right. So, and these videos or these images have been used in training different types of foundation models in 2D or video, including image diffusion models, video diffusion models, and vision language models, like or self-supervised. Actually, Dino is not it's self-supervised. In this work, to distill as much as possible of object intrinsics from these pre-trained Dino features as well as image and video diffusion models. So you may recall that there has been this work pretty well known, and I think it still has a lot of values, but there's a lot of potential that hasn't been fully discovered is in SDS, right? In score decision sampling, people try to distill 3D structures out of 2D pre-trained models. And it has quite some problems in different ways, and there's some other reasons that it's not as popular, but it should be a bit more popular if we can address those problems. But one of the problems that will partially address, but not fully, is diffusion priors, they capture what is going to be the most likely image. And if you want to get a 3D structure out of 2D, then the most likely case of seeing a dog is seeing the front of the dog, right? So you get a dog with multiple faces, right? So that's what people call this Janus problem. Okay. Well, it's not like this. This is an early example, right? Now you could do multi-view fine-tuning or stuff like that to address them, although not fully, right? So even with the most recent like VO3, you still see some of these problems about lag disappearing and stuff like that. But this is an early example which doesn't work as well. But I think it highlights the problem. But then in 4D, you have a similar problem. So what is the problem here is you don't have a temporal structure, right? So then if you ask the system or diffusion model to generate rose blooming, because it doesn't have any condition about time, it's going to generate roses, even if it doesn't have the Janus problem in different views, it's going to have the Janus problem over time. That because people always like to take a beautiful rose, no one's going to take a wilting rose, right? So if I do that, I just use vanilla score decision sampling, and I'm going to get these roses I'm seeing from different viewpoints. You can see that different viewpoints is actually fine, right? It's like, every view, it's a bit multi-view consistency is fine. But then this is actually a video from different viewpoints. You can see there's no motion. It's always this fully built rose, right? Because that's the most popular, well-represented data in a diffusion model. So how can we address that, right? Because we want to distill a dynamic structure out of our pre-trained video models. So our idea is to condition it, just to add some conditioning. So you have an intermediate 4D representation that's a conditioning. So the condition itself, it doesn't only take, just like you can condition the diffusion model, say I have a depth map or whatever, or dino features, and I can condition it, and then or clip features, I can condition it to generate some specific things or controlling object layouts. But now the condition not only take the views, you also take time, right? So it's like, is it the bud at the very beginning process or the blooming process? That's different stages. So we train a neural network, using some time-lapse video as the guidance. You can extract these dino features, left is dino features from, let's say, a time-lapse video of growing process of the flower. You train a neural template, which takes the condition of the input viewpoint, the camera viewpoint, and also the time, and try to produce the corresponding dino features of the rows at a particular stage. Right. So if I condition it at the very beginning, I'll see like a rose that's not, it's maybe this is like fully blown. And in the wilting process, if I condition it to the end, take a different time, you can see the rose just goes down. Right. So that gives you the intermediate representation that's required, and then you can use it to condition the diffusion model so that it can now generate what a rose is supposed to look like at the very beginning, in the middle, and at the end. And once you have that, now you can use score decision sampling to distill the guidance from the video diffusion models so that you can train this thing that you really want to optimize, which is in this thing we call this 4D hyperfields. So which is a 4D hyperfield is something that you can query similarly using a viewpoint as well as a time point. And it will be able to generate the intrinsics you want to get, the digital twins of the objects. You can render just like a neural fields, like a nerve, right? You can render it, but now you can also query with time. So it's a temporal neural fields. In some sense, you can think about it that way. But also the output is not radiance, it's the intrinsics, like object geometry, normals, and albedos. So in that sense, you have a 4D digital twin. You can query this implicit representation, you can get these things, you can take the temporal object intrinsics, let it go through differential rendering, physics-based differential rendering. You can render images. But then if you remember, we just said we have a neural template. So you can say at the very beginning, oh, how the rows should be like. At the end, how the rows should be like. And I can improve this process and learn to optimize this hybrid 40 field by applying SDS on the diffusion models. But the diffusion models are taking the intermediate representations of these dynamic features as guidance, right? So that I'm not only to just still improve the 40 field to make it always look like 3D boom rows. I'm actually improving this 40 field so that it can generate rows at the corresponding stage if I condition it on the corresponding time point. Okay, so that's the whole story. It's a bit complex, but so you want to maintain semantic post correspondence at different times by these conditioned destination. Happy to talk about it more offline though, because I think I'm almost running out of time. And this is again led by Chen, who is my PhD student. And we can compare that with some other 4D generation methods. You can see that it is capturing dynamic process much better. Again, this is a real digital twin, so you can see it from different time point, different viewpoint. You can render it under different lighting conditions, stuff like that. Okay, so very quickly, everything we talk about here has been about object geometries and textures and maybe some autonomous motion. One thing we haven't talked about is their physics. In the narrow definition of physics is geometry is also physics, but the narrow definition of physics is their physical properties, which is actually very important if you want to think about objects or build digital twins that can not only autonomously grow and move, but be able to respond to external perturbations or external actions correctly. So the next problem we'd like to solve is how can we have action condition dynamics prediction of 3D objects, right? So in the case of again, a flower, so if we can reconstruct it in 3D, we get a 3D representation of a flower that can be Gaussians from a single image or LGM or anything like that. You want it to not only just grow, you want it to be able to respond to external actions. That this is our output, right? If I poke it here, if I pull it there, how the scene is going to look like. And you really want to do action condition prediction so that you can poke and interact with different ways, right? So the challenge here and the problem we want to solve in this setup is now you want to also get physical object properties, right? In this particular case, probably like stiffness. So not just geometry and texture and the growing process or lifespan, but also the actual physical properties. And it turned out that the problem is not as easy as it seems to be, because you may feel like, oh, I just randomly sample some physical properties and density or Young's modulus should be okay. But just like vision is hard, it's like the realistic distribution of object geometry is very narrow. The realistic distribution of object physical properties is also very narrow. So if just randomly assign physical properties, it's not going to look good. And also, this thing is high dimensional, right? It's heterogeneous. So it's not like every part has the same physical properties. The stem and the petals, they have very different physical properties. Therefore, it's not as easy to just randomly generate physical properties and they're all going to look kind of bad, right? So how can we actually get much better physical object properties from these pre-trained models? So in this work called FitStreamer, which is led by my PhD student Koben and Tianyuan, who is a PhD student at MIT with Bill Freeman. So what we did is also another very simple idea is, let's say you already have a 3D space in Gaussians. You can render it into a single image. You can send the image to video generation model. You get a reference video. The reference video is supposed to look realistic, right? But then just a video. It doesn't tell you any physical properties or geometry, but it's a realistic video. At the same time, you can take a material field or physical property field that is something you would like to optimize. And you can let it go through a differential simulation pipeline, which I don't have time to talk in detail, but differential material point methods, which is very popular in simulating soft bodies. You can let it go through this pipeline. And you're going to get, as I said, if you don't have a very good estimation of physical object properties, you can get a rendered generated video, which doesn't look as realistic, but it is physics-based. So then you can compare the two. And surprisingly, even if you just compute L2 loss directly in the pixel space, the L2 loss is powerful enough that you can use gradient-based backpropagation to update the optimization of the material field. Eventually, you will be able to get material fields or with physical property fields that are close enough so they actually produce, when you render the video from different viewpoints, it should look like what a video generation model looks like, right? So, but now you actually get physical properties in addition to the geometry. Okay, so some more results. Flowers interacting with, because NPM is very good for soft bodies, we have actually more results on soft bodies. And we actually even have a comparison with the ground truth. So the first row is a column is a ground truth. which we got by having a fan next to the flower, and the second is our results, and third and fourth are baselines. You can see that with the right physical property estimations, it just works a lot better. Okay, so after that, Coven also tried to think about, is that possible for us to not only just work on soft bodies, but also look into more challenging cases. So the particular case, which I only have time to show one slide, is he also looked into how we can simulate fluids, right? So they can reconstruct and build digital twins. Well, I don't know what that means for a digital twin, but it's indeed a virtual 4D visual physical simulation for fluids. So they can go from a single video, you can try to reconstruct the 3D fluid fields, which is for appearance, but also the physical fields, which is here in this case the velocity, so that you can render from different viewpoint. And then you can also do action condition prediction, just like you can put a wing next to the flower and see how it waves. You can also put a wing to the fluid field and see how it's going to respond to the interactions. Yeah. Okay. So can I have I think I should have a few more minutes because I started late. My time said it's only 25 minutes now. Yeah. Oh, well, after there's lunch, right? Yeah. Yeah, so it's fine. Okay, thank you. But people should go and have lunch if you want. That's fine. I'm not offended. Feel free to leave. Okay. So yeah, let me use my final maybe 3 minutes. Okay, to wrap up by showing just one last work. That is, as I said, Cohen worked on this flower thing, and you can poke it, and you can work on a fluid thing. But the real world is complex, right? So we have soft bodies, rigid bodies, and fluids and flows and everything. So is it possible for us to, instead of having independent separate work for fluids or soft bodies, have a one unified framework? So I can build digital twins of not only objects, but also worlds with objects of different matters. So he had a separate work, again, Cohen, had a separate work, which I don't have to talk about. It was on static scene generation. So what he can do in that paper is you can take a single image and users can upload a picture and the system will turn it into 3D. And then now you can in close to real time, explore and navigate in a 3D space. And you can type in things you want to see. For example, I can say on the left, I want to see an Asian courtyard. And then I can then move to the right and I want to see a future city. Right? Everything here is in 3D so that you can move around and stuff like that. Okay. So, but here everything is static. So now we thought about how can we integrate the dynamic structures like fluids or film objects into this 3D world. Right? So in this final piece of work, what we're trying to do is we take a single image and we want to generate a dynamic 3D action condition predictions, right? So of the scene. So you can see that I can drag this rubber duck and I can have the rubber duck interact with the fluid below it. Right. So I have a video that quickly summarizes what we can do in this work, which is actually going to be presented, I think, tomorrow at ICCV this year. Yeah, I think one thing I want to highlight is it's important to be aware that this is a 3D representation or a 4D representation. So although it looks like a video, it's not just a video. You can render the video from this viewpoint. You can render the video from a different viewpoint. So you can move the camera as well. Okay, so the main message here is the same. It was like, oh, I have two paradigms. One is about using simulation or in the loop, and one is not. But they have their own strengths, right? Simulators, they're, as I said, they're often not very accurate. Even if you assume perfect vision, you have perfect materials and estimation. And second, the vision itself is very hard, right? So there's often impossible to get perfect geometry, but also physical property estimation from a single image. So even with perfect vision, it's not perfect, simulation, and vision itself is hard. But the strength of a simulator is it directly take action condition input, right? I can apply any type of actions, I can simulate what's going to happen. And video models, in some sense, are good in different ways. because video models are supposed to be very general. You can take any objects, any images, any type of materials. They should be able to do a lot of completion because they have very good common sense and visual parts, even from a single image with missing regions or occlusions, you can complete everything. But the issue with video models is they cannot really take action to the input. You can say maybe VO3 can take, no, Genie 3 can take a little bit of going forward, backward, and some language conditions as the input. But that's very different from the actions you really want to have in the physical simulation or eventually for robotics, because the action space is so much higher and you have so fewer data. So they can't really take action conditions as input. So our idea is just try to put together two. Maybe we have some hybrid visual physical generative simulator. So if we go back to this two paradigm I said at the very beginning, right? You have a self-supervision and you have a distillation. So I think in some sense we're trying to combine the two. We're thinking about how can we fuse these two paradigms so that you can distill from video generation models these physical properties, but also think about how physical properties should be used as a conditions to guide these visual generators to make it more realistic, physically possible. And the visual generators themselves should give you visual realism so that you get the best of both worlds. So in a single slide, I can summarize the idea behind this work as I have a single image. I want to build this hybrid generative simulator that combines a physical simulator and a video generator. What we did is you first take this image, you reconstruct in 3D, let's say using Cohen's earlier work, like a 3D reconstruction. It's not going to be perfect. You're going to have a lot of missing regions and some artifacts. But the coarse 3D reconstruction might be okay. At least you can first send it to a physical simulator. So you can get a coarse simulation. So what is going on here is, I can play this. You have a core simulation that roughly gives you an idea of, intuitively, in some sense, is like how physics is supposed to work, right? The flow and the fluid, how it is supposed to interact with the shoes. If you work a bit more closely, you realize they have all the artifacts, right? On the shoes, you can see all these Gaussian artifacts and stuff like that. So it's definitely not perfect. But the rough physical prediction might be enough. You can use it as a condition for the video generator. You can extract optical flow or depth map or stuff out of it, use it to condition your video generation so that the video generator will be able to give you a much more realistic simulation. But it is just a video, right? That doesn't have 3D. It's just a video, but it looks perfectly realistic. So finally, what you can do is you can use that to refine your physical simulation. You can re-optimize, again, because everything is different for simulation and rendering, you can re-optimize your physical simulation to make it match the videos generated by the video generator, right? So then finally you get the best of both worlds, because first it looks a lot more visually realistic. Second, it is still physically possible, right? Because you're now doing better state estimation and it still goes through physical simulation. And finally, it's all in 4D, so that you can move the camera. You can go forward, backward. It's not just a video, right? So that really gives you the best of both worlds. And you can see all these results of different phenomena: rigid bodies interacting with fluid, soft bodies, trees, sand, rigid bodies interacting with each other, or fluid flows. So you can take multiple actions, and you can see how the shoe is going to disturb the flow as well. And because you take action condition predictions, you can go from the same scene, apply different actions, and see how it's going to work. Okay, so this hopefully some very general version of physics-based action condition digital twins of objects, of different matters, but also the worlds. Again, this is by Coben and also my first year PhD student, Jiajun. Okay, so to summarize, I think there is always this question about to get digital twins out of visual simulation or video generators or physical simulation. Then what are the things that we want to model, and how can we get out of them? What's the role of physics-based simulation, which we already have knowledge about digital twins are supposed to be modeled or rendered, and what's the role of protein foundation models, and to what extent they have learned the things we care about, and how can we integrate them? So when we're trying to build a distill digital twins, we're thinking about what are the universal, or I would say really universal optic intrinsics that shape materials, and these are things that applies to every object and has been studied for decades in physical simulators and renderers. So we want to really leverage those. And they're causal, right? So if you change something, you change physical parameters, you change the external actions, it's very easy for you to simulate how the scene is going to respond to these actions. So it's causal, physical, and universal. And of course, there could be different paradigms, as I said, of how can they integrate with deep learning. But it does allow you to, either through self-supervised learning or through leveraging pretraining models to use a lot of in-the-wild data and use differential simulators, as we have shown. And we haven't used much synthetic data, but that could potentially be very useful too. And finally, it's naturally interpretable because this is physics and stuff like that, and give you all the controllability as we have shown. Thank you.